What if the ground beneath one of the world's most feared earthquake zones is not simply locking up for a future disaster, but quietly stretching, cracking, and rearranging itself in ways that might actually reduce the risk of an unimaginable catastrophe? What if the slow tearing of Earth's crust, a process that sounds alarming at first glance, could be part of a natural safety valve built deep into the planet's mechanics? And what if understanding this process could change how we think about earthquakes along the Pacific coast forever? Along the storm-lashed margin of the northeastern Pacific Ocean lies one of the most intensely studied geological systems on Earth, the Cascadia margin and its underlying Cascadia Subduction Zone. Here, the small but geologically powerful Juan de Fuca plate moves steadily toward and beneath the massive North American plate. This convergence is not dramatic on human timescales. It occurs at a speed roughly comparable to the growth of fingernails, yet over thousands and millions of years. That slow motion reshapes continents, builds mountains, triggers volcanic eruptions, and generates some of the most destructive earthquakes known to science. For decades, geologists have focused on the possibility of a single massive rupture along this boundary, often called a megathrust earthquake. Such an event could release centuries of stored strain energy in one violent episode, but recent studies have revealed something more subtle and in some ways more reassuring. Instead of behaving like a rigid slab that simply bends and locks, parts of the descending oceanic plate appear to be tearing apart in deep, complex patterns. And these tears are not sudden rips like fabric being pulled. They form gradually through mechanical stress, heat, pressure, and interaction with fluids circulating through the crust and upper mantle. To understand why this tearing might be considered good news, it is important to first picture how subduction normally works. As an oceanic plate approaches a continental margin, it begins to dive downward at an angle. The leading edge scrapes against the overriding plate, forming a long zone of friction. This zone can become locked, preventing smooth motion. When the plates finally slip, the sudden release produces an earthquake. However, the plate that is descending is not uniform. It contains faults, fractures, ancient volcanic ridges, and zones of weakness formed long before it reached the subduction zone. These inherited features influence how the plate bends, cracks, and ultimately breaks apart as it sinks. One of the most important forces acting on the subducting plate is bending stress. As the plate approaches the trench, it must curve downward. Imagine trying to push a thick wooden board over the edge of a table. The top surface stretches while the bottom surface compresses. In tectonic plates, this bending creates tension cracks on the upper side. Over time, seawater seeps into these cracks, altering the minerals and weakening the rock. This process is known as hydration. When hydrated minerals are carried deeper into the earth, they release water under increasing pressure and temperature. That water reduces friction along faults and promotes further cracking. In the Cascadia region, detailed mapping of the seafloor and deep seismic imaging have revealed networks of faults that cut across the subducting plate. Some faults run parallel to the trench, while others slice across it at angles. These structures allow the plate to fragment into segments rather than behaving as a single unbroken slab. The tearing process is therefore not chaotic. It follows the lines of existing weakness, guided by stress patterns generated by plate motion, gravity, and the pull of the sinking slab itself. Another key mechanism involves temperature differences within the plate. Oceanic crust forms at mid-ocean ridges and cools as it moves away from them. By the time it reaches a subduction zone, parts of the plate may be colder and stronger than others. When these contrasting zones are forced downward together, they respond differently to stress. Stronger regions may remain intact, while weaker zones crack and deform. This creates uneven sinking and can lead to partial separation between plate segments. Over long periods, these separations grow into significant tiers extending tens to hundreds of kilometers. Fluid movement also plays a central role. As the plate descends, Increasing heat drives chemical reactions that release water and other volatile substances. These fluids migrate upward into the overlying mantle and crust, lubricating faults and altering rock strength. In some cases, they trigger slow slip events, where plates move gradually over days or weeks instead of snapping suddenly. Such slow motion releases energy without producing destructive shaking. The presence of tears and fractures within the plate provides pathways for these fluids, effectively spreading stress over a wider area. Geophysicists studying Cascadia have observed that certain sections of the subduction zone appear to be less tightly locked than previously thought. This does not mean large earthquakes are impossible. Rather, it suggests that strain may be distributed through a combination of slow slip, micro-fracturing, and deep plate tearing. When a rigid system begins to fracture internally, it often loses the ability to store enormous amounts of energy in one place. In geological terms, fragmentation can act like a pressure release mechanism. The geometry of the subduction zone further influences how tearing occurs. The descending plate does not plunge straight down. It dips at an angle that changes along the length of the margin. Where the dip becomes steeper, gravitational forces pull more strongly on the slab, increasing the likelihood of stretching and cracking. In regions where the dip is shallower, friction with the overriding plate dominates, potentially leading to stronger locking. The transition between these zones is especially important because it concentrates stress. Many scientists believe that tears often initiate in such transitional areas. Another factor is the presence of seamounts and underwater ridges on the oceanic plate. These features act like bumps on a conveyor belt entering a narrow gap. As they are forced beneath the continent, they distort the surrounding rock and create localized zones of weakness. Over time, repeated deformation around these obstacles can lead to structural failure of the plate itself. This contributes to the patchwork pattern of intact and fragmented segments observed beneath Cascadia. The tearing process also affects the mantle flow around the sinking slab. When the plate remains continuous, it behaves like a barrier that channels hot mantle material around its edges. But when tears form, mantle rock can circulate through the gaps. This circulation changes temperature distribution and influences melting processes that feed volcanic systems on land. In Cascadia, volcanoes such as Mount St. Helens and Mount Hood owe their activity partly to fluids and heat rising from the subducting plate. Plate fragmentation can modify how and where this heat transfer occurs. From a mechanical standpoint, tearing can be compared to scoring a sheet of metal before bending it. The scored lines guide deformation and prevent uncontrolled failure. In tectonics, faults and fractures play a similar role. They define where strain will accumulate and where it will be released. If enough of these features exist, the system may experience frequent small adjustments instead of rare, catastrophic ruptures. This concept does not eliminate seismic hazard, but it reshapes expectations about how energy builds up in the crust. Deep earthquakes occurring within the subducting slab provide further evidence of internal deformation. These events often happen far below the surface, at depths where high pressure should normally prevent brittle failure. Scientists think that dehydration reactions combined with stress from bending and stretching allow rocks to fracture even in such extreme conditions. The distribution of these deep quakes helps map the shape and integrity of the plate as it descends. In Cascadia, patterns of seismicity suggest zones where the slab is breaking apart or thinning. The long-term evolution of a subduction zone can also involve slab rollback. This occurs when the descending plate sinks more steeply and retreats oceanward. Rollback increases tension within the plate, making tearing more likely. It can also stretch the overriding crust, forming basins and faults on land. Geological records in the Pacific Northwest show episodes of crustal extension that may be linked to changes in subduction dynamics over millions of years. Another subtle but important process is shear heating along faults. When rocks slide past each other under pressure, friction generates heat. This heat can weaken minerals and encourage further slip. If a plate is already fractured, shear heating along multiple fault surfaces can distribute deformation across a broad zone. Instead of concentrating stress at one locked boundary, the system becomes more diffuse. This diffusion is one reason scientists are cautiously optimistic about the implications of plate tearing. Modern research relies heavily on ocean bottom seismometers, satellite measurements of ground motion, and advanced computer simulations. These tools allow geologists to visualize how stress moves through the crust and mantle. Models show that a segmented slab can reduce the size of potential rupture zones, while a continuous locked interface might produce a single earthquake spanning hundreds of kilometers. A fractured interface may break in smaller sections. Each section would release less energy, potentially lowering maximum shaking intensity. However, the relationship between tearing and seismic hazard is complex. Fragmentation can also create new fault surfaces capable of generating earthquakes. It may alter tsunami potential by changing how the seafloor moves during ruptures. The key point is that geological systems rarely behave in simple, predictable ways. Tectonic plates are dynamic structures shaped by competing forces. Tearing represents one pathway through which those forces find balance. Understanding these mechanisms requires integrating data from many scientific fields. Structural geology examines the orientation and movement of faults. Geochemistry studies mineral reactions that influence rock strength. Geophysics measures seismic waves to image deep structures. Together, these disciplines reveal a picture of Cascadia not as a static ticking time bomb, but as a living system constantly adjusting to stress. One of the most intriguing discoveries is that tearing may occur in stages. Initial cracks form near the surface as the plate bends. These cracks deepen over time, eventually linking with older faults formed at mid-ocean ridges. As the slab sinks further, dehydration reactions and temperature changes promote additional fracturing. The result is a layered pattern of weakness extending from the seafloor to depths of hundreds of kilometers. This progressive evolution helps explain why the subduction zone does not behave uniformly along its length. In some areas, the plate appears relatively intact, maintaining strong coupling with the continent. In others, it shows signs of thinning, segmentation, or even partial detachment. Such variability affects how seismic waves travel, how volcanoes erupt, and how landscapes evolve. It also means that hazard assessments must consider local geological conditions rather than treating the entire margin as a single entity. Ultimately, the idea that Cascadia is tearing apart should not be interpreted as an immediate threat or a guarantee of safety. It is a reminder that Earth's crust is constantly undergoing transformation. The slow breakdown of a subducting plate is part of a broader cycle of creation and destruction that shapes ocean basins and continents alike. By studying this process in detail, scientists hope to refine predictions of earthquake behavior and improve resilience strategies for communities living along the Pacific coast. In the grand timescale of geology, tearing is not a sign of weakness, but a natural expression of planetary motion. It redistributes forces, alters pathways of heat and fluids, and influences how energy is stored and released. For geology enthusiasts, Cascadia offers a remarkable natural laboratory where these processes can be observed, modeled, and debated. The more we learn about the subtle mechanics beneath our feet, the clearer it becomes that even seemingly alarming phenomena can carry hidden benefits within the complex machinery of Earth. Beneath the restless waters of the northeastern Pacific, the slow disintegration of the descending slab continues to influence a wide range of geological processes that extend far beyond the immediate boundary where plates meet. One of the most fascinating of these processes involves episodic slow slip and tremor activity, a phenomenon that has reshaped scientific understanding of how tectonic strain is released. Along the Cascadia Subduction Zone, instruments have detected periods during which sections of the plate interface move gradually over the course of several days or weeks. These motions are too gentle to produce strong shaking at the surface, yet they release measurable amounts of accumulated stress. The connection between slow slip and plate tearing lies in how fractures within the descending slab influence fluid pressure and fault strength. When mineral transformations occur deep underground, water is liberated from hydrated rock. This fluid does not remain trapped. It migrates along cracks and fault zones, increasing pore pressure and reducing the friction that normally keeps plates locked together. In regions where the Juan de Fuca plate is heavily fractured, the network of pathways for fluid flow becomes more extensive. This promotes more frequent episodes of gradual movement rather than long intervals of total locking followed by sudden rupture. Geologists studying seismic tremor patterns have noticed that these signals often cluster near the transition between strongly coupled and weakly coupled segments of the plate boundary. This transition zone marks the depth where temperatures become high enough to change rock behavior from brittle fracture to ductile flow. The presence of tears and segmented slab geometry modifies how heat is distributed in this region. Where gaps exist in the slab, warmer mantle material can circulate upward, raising temperatures locally and encouraging ductile deformation. This process reduces the likelihood that stress will accumulate in a single massive block. Another important mechanism tied to slab tearing is the redistribution of gravitational forces within the descending plate. As an intact slab sinks into the mantle, its weight creates a pulling force known as slab pull. When the slab becomes segmented, that force is no longer transmitted evenly along its length. Some portions may sink faster than others, leading to stretching and internal shearing. Over long timescales, this differential motion can cause the slab to thin or even partially detach in certain areas. Such detachment alters the stress field both offshore and beneath the continent. Changes in stress fields can influence how faults develop in the overriding crust. In the Pacific Northwest, geological evidence shows episodes of crustal extension interspersed with periods of compression. This alternating pattern is thought to be linked to variations in subduction dynamics, including slab rollback and tearing. And when rollback occurs, the hinge point where the plate bends moves oceanward, effectively pulling the upper plate apart. This stretching can create basins and normal faults that accommodate strain without generating large earthquakes. Mantle convection patterns also respond to the evolving geometry of the slab. In areas where the plate remains continuous, hot mantle rock is forced to flow around its edges, focusing melting processes that feed volcanic arcs. Where tears open, mantle flow can rise directly through the gaps. This creates more diffuse zones of melting and can change the location and chemistry of volcanic activity. The volcanoes of the Cascade Range, including Mount Rainier and Mount Shasta, are influenced by these deep processes. Their magma sources reflect variations in temperature, pressure, and fluid content tied to slab structure. Tearing also affects how seismic waves travel through the earth. When waves encounter intact, cold slab material, they move faster due to the higher density and rigidity of the rock. In contrast, fractured or partially molten regions slow seismic waves and scatter their energy. By analyzing these wave patterns, geophysicists can create three-dimensional images of the slab's internal condition. In Cascadia, such imaging has revealed complex shapes suggesting that the slab is not simply bending downward, but undergoing progressive fragmentation. On a broader geological scale, plate tearing plays a role in the life cycle of ocean basins. As slabs break apart and sink, they contribute to the recycling of crustal material into the mantle. This recycling influences mantle composition, and ultimately the formation of new crust at spreading centers elsewhere on the planet. The Cascadia margin therefore represents one stage in a continuous global system of tectonic renewal. The apparent instability of the region is part of a long-term balancing act between creation at mid-ocean ridges and destruction at subduction zones. Some researchers have proposed that segmented slabs may lead to a series of moderate earthquakes rather than a single catastrophic event. The idea is that each segment accumulates stress independently. When failure occurs, Rupture length is limited by structural boundaries such as tiers or zones of altered rock. This concept is supported by historical and geological records showing variability in earthquake size and frequency along subduction margins worldwide. While it does not eliminate the possibility of large earthquakes, it introduces a more nuanced understanding of seismic potential. Another subtle consequence of slab tearing involves the generation of deep mantle earthquakes. At depths exceeding several tens of miles or over 100 kilometers, high pressure should prevent typical brittle fracture, yet earthquakes still occur within subducting plates. Scientists believe that dehydration reactions, combined with stress concentration around tiers, allow sudden slip even under extreme conditions. These deep quakes provide clues about the internal state of the slab and help refine models of how it deforms during descent. The cumulative effect of all these processes is a tectonic environment characterized by complexity rather than uniformity. Instead of a single continuous fault storing energy for centuries, Cascadia appears to consist of multiple interacting systems. Fractures guide fluid flow, temperature variations influence rock strength, and mantle circulation responds dynamically to changes in slab geometry. Together, these mechanisms create a feedback loop in which deformation in one area alters conditions elsewhere. For geology enthusiasts, the tearing of the Cascadia slab highlights the importance of viewing Earth as an evolving machine rather than a static structure. Every crack, tremor, and subtle shift reflects deeper adjustments occurring far below the surface. While the term tearing apart may sound alarming, it actually describes a process that can distribute stress more evenly across the plate boundary. By preventing the buildup of extreme strain in a single location, fragmentation may reduce the maximum energy released during future earthquakes. In this way, the slow mechanical breakdown of the subducting plate can be seen as part of a natural regulation system. It reshapes the pathways through which heat, fluids, and forces move within the planet. It influences the rhythm of seismic activity, the evolution of volcanic arcs, and the long-term stability of continental margins. Cascadia, far from being a simple danger zone, stands as a vivid demonstration of how destruction and balance coexist within Earth's tectonic engine. If you found this video informative and engaging, please take a moment to like, share, and subscribe to the channel. Your support helps this content reach more viewers who are passionate about science and the powerful forces shaping our planet. Also, make sure to tap the hype icon to boost this video in the algorithm and help it reach a wider audience. Every action you take helps this channel grow and continue producing in-depth geology content. Thank you for watching and for being part of this learning community.